All right, so take a second to look at this. This is these are the relationships between the field strength, so gravitational field strength, potential and distance, electrical field strength, electrical potential and distance, right? There's a tricky little minus sign, which in general I ignore, but I'll show you where it comes from. It is actually a vector thing, and it's kind of cool, and some people are going to use it and some people aren't, okay? So this is, of course, this is G, this is newtons per kilogram, right? This is here, this is, what, joules per kilogram? That's our gravitational potential, and then this is a displacement. That's just meters, right? Okay. Notice that the difference between a joule and a newton is a meter, right? So, unit-wise, we're in good shape here. This is newtons per coulomb, right? So this is our electric field. This is our electrical potential, which is, of course, joules per coulomb or volts, right? And again, that's just meters, right? Now, remember that, like in this case, electric field is force divided by charge. Also remember that, let's see, work is equal to charge times the change in electrical potential, right? Okay. Remember that work is force times distance. So force times, in this case, I'll use R as my distance, right? That equals Q times change in potential, electric potential, right? Okay. So then if I just sort of mess around with this, I'm going to divide this side by Q and divide this side by R, right? I get F over Q is change in V over R. And then, of course, I don't have the minus sign in there, right? So let's just put it there, right? I'll show you where it comes from, though. It has to do with these vectors, right? So this is how you can get that. This is, of course, our electrical field. And we can do the same thing over here, right? G is equal to force divided by mass, right? And work is equal to mass times change in gravitational potential. Work is also force times distance. I'm using R, so we can do that, right? So force times change in R, that equals mass times change in Vg, right? Well, let's put the m over there and the R over here, right? And we get force over mass, which is G, right? Is equal to the potential over R, right? So basically that's where these formulas come from, okay? Now why there's a minus sign there, let's do an example problem and I'll show you why, okay? So let's look at this guy. You have a gravitational field strength of 9.81 newtons per kilogram, right? Well, that's going to be down, right? Won't that be negative, right? Okay, so we go negative. Let's figure it out first, okay? So we go negative 9.81 newtons per kilogram because it's down, right? That equals negative, and then the change in potential. And then don't we go upward 1.85 meters, so that's positive 1.85, right? So now I can do a little, this is meters, right? Okay, and I want to find this gravitational potential, right? So I'm going to go, basically it's 9.81. The basic math is not pretty simple. 9.81 times 1.85. I get 18.1485, and our units, by the way, are Newton meters over kilograms, which, by the way, a Newton meter is a joule, right? Notice that I end up with a positive number. Do you see that? Because the minus signs go away like that. I end up with a positive number, and this makes sense because I'm lifting the mass upward. The change in gravitational potential would be positive, okay? So that's why the plus sign is in there, or the minus sign is in there, is to make it come out so that it's even. If I go from here to here, if I move this mass that way, a vertical upward distance, the change in gravitational potential has to be positive. And if I put the minus there and there wasn't a minus there, it wouldn't be positive. Okay. Let's look at this thing, and then I'll explain where why there's a minus sign there. Again, I generally ignore this minus sign, right? But let's figure this out, right? So E is just change in, right, over R. And again, I'm going to ignore the minus sign. So it's 12 volts. This is, by the way, how you create electric fields, right? Divided by 0.0150. So 12 divided by 0.015 is 800. Okay, 800 volts per meter, which is interesting, right? It's like, gee, is that really a unit of electric field? And indeed it is, right? A volt per meter. Remember, electric field, we are accustomed to, newtons per coulomb, right? But a volt is just a Newton meter per coulomb per meter. right? So a volt is a joule per coulomb. A joule is a Newton meter. Notice that the meters go away, you end up with newtons per coulomb. So a volt per meter and a Newton per coulomb is the same thing. Let me tell you that volts per meter is a more common expression of electric field, okay, just simply because we do it by making a voltage change over a distance, okay? Now, then the question is, why is there a minus sign here? Let me just show you this, okay? Let's imagine that we have a positive plate here and a negative plate there, right? Okay, the electric field, by the way, here is, let's see, a positive charge would go up. The electric field is up. Yeah, okay. So, is that right? Yeah, the electric field is up here. Okay, now if I move something, if I take a charge and I move it from here to here, okay, let's just take a look at this thing. Let's say this is 800 volts per meter, right? And I take some charge and I move it across there. If I move it from here to here, its potential becomes negative, right? So the change in potential is going to be a negative change in potential, right? Yet my electric field is positive, right? Because it's upward. So the minus sign is there to make it so that the change in potential is actually negative. Okay. Let me just show you this. So positive 800 is what this is, right? This thing's positive 800 volts per meter, right? Is equal to the opposite of some change in potential, right? Over R. Well, R is positive. It's positive 0.0150, right? Okay. But if I go from there to there, aren't I moving down in potential, right? And that's why there's a minus sign there, is to make this come out negative. Okay. Again, I generally ignore the minus sign on these things. Okay. Happy hunting.